Well, last time, after the addition rule, we have seen a couple examples, right? To have a union of the probability, we add each part together, then subtract the intersection part. And a couple you have seen already. If the intersection is equal 0, has 0 probability, then it simply means they are mutually exclusive. Right? The events are mutually exclusive, or in other words, disjoint. Alright, let's see some other example. Another one. We're rolling 2 fair dice, and the y to be the sum of 2 dice. I find the probability that the sum is 5 or the first die is 3. But based on the formula, we need to use the addition rule for this union basically. Right, the first part, the sum is 5, the second part, the first die lands on the value of 3. Well, we need to minus the intersection. Of the sum is 5 and as well the first die is 3. So we do the probability separately. Let's do the first one, right? The sum is 5. Well, we have the outcome already, the sum to be 5. We can list it, or we can have a list of the sum to be 5. That is, the first die is 1, second die is 4. Or 2, 3, 3, 2, or 4, 1. Right? That's 4 different cases to make the sum to be 5. Well, we have that 4 outcomes in this event, which rolling 2 dice will have 36 different pairs. That 4 out of 36 will be the probability to get a sum to be 5. Then also the first die is 3. My first die is 3. But when first die is 3, second die of the rolling 2 dice could be any number from 1 to 6, could be any face value. Then it can take value from 3, 1, 3, 2 all the way to 3, 6. That's 6 different outcomes. Therefore, the probability, 6 over 36. And the one extra thing is, well, do we have anything over there, right? To make the sum to be 5 as well, the die have the first value is a 3. Well, we have actually the case is only one case in both of them, that 3, 2, right, is the case. The first die lands on 3 as well as the sum of them give us a 5. So that's one case. The probability will be 1 out of 36. When we simplify it, that 4 plus 6 minus 1, that will give us 9 over 36. Which, if we want that result, can be turned into decimal by 0.25. You could use calculator to divide it, right? That will give us 0.25. Oh, the second part, y equal 2 union y equal 4, find that probability, which is the sum is 2 or the sum is 4. Which, if we're thinking clearly or thinking carefully, when the sum is 2, it cannot be equals 4. Well, let's try to verify it. Right? Let's try to do the same thing, list the outcomes of how the sum to be 2 and how the sum to be 4 to make sure they do not overlap. Of course they will not, but let's see. Right, to be a sum of 2, the first one lands on 1, the second die is also lands on 1. That's the only case it can be possible. And the sum to be 4. Oh, let's see, if the first one lands on 1, the second die needs to be 3. If the first is 2, the second needs to be 2. Also, if the first die is 3, the second die has to be 1. And that for sure is only 3 possible ways to get the sum to be 4. And of course, clearly we have nothing overlaps, which means in the beginning we have said they are disjoint. When the sum is 2, it cannot be equal 4. When the sum is 4, it cannot be equal 2. Right? So, and when we list out that we have verified that they actually cannot happen at the same time. So, simply add them together, or add the probability. That is nothing as union, which we get is, well, 1 out of 36. And 3 over 36, right? This one do not have overlap since disjoint. Then we just add each part probability together. Then we get 4 over 36, which is a 9. Then if we want to turn into decimal, that's 0.1111. Let's see the rest. And the third part is simply asking for the intersection, as we see from the last example. when the sum is of one value, it cannot be the other. So the sum to be 7 and the sum to be 12, well, they have no overlap. If you want to see the outcomes, 7, that will be 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. 6 outcomes. And 12 of the sum that we can only get is 6, 6. But therefore, nothing in common. The probability that will be equal to 0, since they are disjoint each other. Since the sum to be 7 and sum to be 12 are disjoint, then we get the probability equal to 0. Right, that is pretty much the addition rule. Either disjoint or no, we can check by listing or check intuitively. Something is clear that they are disjoint, something is very clear that they are not disjoint. If you're not sure, you can always try to list the outcome and everything will become clear. And let's go to the next part. Multiplication rule and conditional probability, which we can see by some examples. The same table we had used before. That's for the individuals using drug and have test. For the 4 individuals uses and have positive result, and uses drugs and have negative result, not using drug but have positive, not using drug and have negative result. So to find the total, that's 1,000 in total, which 50 uses drugs, 150 not using drug, and 134 in the meantime got a positive test result, and 866 got negative test result. My total, either way, that's 1,000. Let's see. So instead of focusing on the whole sample, what we are focusing on, or what we're using, is only the 50 subjects who use drugs, like the first 2 rows only. 44 positive, 6 negative, in total 60 uses drugs. That's very simple. I find the probability that randomly select one person, I have positive result. what's the probability the randomly selected one person has a positive test result from, of course, the only 50 subjects uses drugs. Right, so from 50 subjects uses drugs, that is 44 has positive test result. Right, so when we select one out of it, that we have 44 ways, right? 44 possible selections. Therefore, the probability here will be 44 over 50. Right, because we're focusing on the 50 people or subjects uses drugs, then that's the amount. 44 is the amount of them who uses drug. And then we turn into decimal, that's 0.08. Not pretty, not that hard, right? We have focusing on the first row, and then from that first row, we have category that positive and negative result. We need one to positive result out of those people who use drugs, that's 44 over 50, so we have one selected. Randomly select two persons without replacement. Without replacement means you not put it back. When I have the markers, when I have the eraser, I have calculator, I select the red marker out, then save it aside. Then instead of having a red marker, I do not no more have red marker in my selection, then whichever left over is left over. Right? The left marker, the other things I have. And so without replacement, whichever you do for the first one, for the first person, you actually affect your result for the second. Right? So let's see what they ask. Or they want to find the probability to get first person as positive test result, second person as a negative test result. First is positive, second is negative. Well, they actually have two steps during this event, right? And for completing this step, we get one complicated event that we can do one by one and multiply the probability together. Right? That's somehow the multiplication rule when we do event step by step. Like the event is select two persons, and we need to do it step by step. The first and the second depend on what do we need. So if we're doing it step by step, we can multiply the probability of individual together. That's the thing. So first is positive. It's we have just seen it already. That is select 44 positives out of 50 in total. Then multiply with the second probability. The second we want is a negative. Now without replacement, I select one positive out of the 44 people, right? 44 in other words persons, there are 43 positive results remain still, and for the total, instead of 50, that is 49 remains, right? And it doesn't affect the negative. The negative is still 6 of them, right? So if we want select the second to be a negative test result, we're actually still selecting 6 different persons, right? We still have 6 different ways to select that negative persons out. But out of, instead of 50, now we have 49. Not making sense, right? Without replacement, the one you select, you put it on the side. You not put it back. So instead of 50, the person you select already, so that no more 44 positive, that's 43 positives left over after the first step, and no more 50 individuals, that will be 49 individuals left over, and the negative will still be 6. Right. So leave like that is fine. If use calculator to convert it to decimal, it's also fine. That is 0.10775 or 0.1078. Usually, while keeping 4 digits decimal will be appropriate. Right, less will be also okay, but like this is good also. Right, so question C. Oh, we still select 2 persons without replacement. We want to see, well, how do we get when they both have negative test results? Right, so still step by step. Both are negative means, well, the first is negative and second is negative. Right, that's what both negative means, right? The first is negative as well as the second is a negative. That we can get is, well, the first negative, there are 6 negatives in the pool, right, out of 50. But now, right, instead of 6, when we select the first one to be negative, that will be only 5 remains, right, instead of the 6. That's 1 less, so we get 5 remains, and instead of the 15 total, that will be 49 because we have without replacement. Okay, 6, 50, 5, or 49. That you can also convert into decimals. That's 0.01224448 and so on. That's without replacement. Of course, if you're thinking, well, that's another type of with replacement, then everything will be replaced back. Right? The one you select, it will put back. So nothing number will be changed. If the first is positive, second is negative, that will be 44 over 50. Then put the person back. Then for negative, that's still 6 over 50. Right, for both negative, that first one is 6 over 50, but the person is selected, put it back. The second person will still be 6 out of 50. Right, the same way to multiply it. But what we can see here is when we select without replacement, the first one of the probability actually affects the probability of the second, even though we can see here asking for same thing, both are negatives, but when we do step by step without replacement, actually affects. That's the way. Well, let's see the next question. Right, 20 couples give birth to 20 babies. Of course, assuming that's equally likely to get boy or girls. Find try to find what all 20 babies are girls. Well, which means the first is girl, second is girl, third is girl, all the way to the 20th is girl. And again, right, that's step-by-step event. The first one coming out, then the second coming out, then all the way to the 20th, which for the 20 different couples, right, the likelihood for them doesn't affect each other. You cannot say, well, the first one is girl, then second couple is more likely to have girl. You cannot say that, right? The likelihood is still fixed, right? It's still fixed, assuming independently, right? That's another word. But assuming that doesn't affect each other, and well, that's the assumption we can make. Right? The 20 babies, all 20 babies are girls. That means the probability of first is girl, second is girl, turn all the way to 20th is girl, which if we do step by step, that is the probability of first is girl, individually, right? Probability of first one is girl, second one is girl, all the way to the probability of the 20th is girl, which with assumption equally likely for boy and a girl, that's a half for each couple. I will multiply 0.5 simply 20 times. That 0.5 is the probability of a couple have a newborn baby to be a girl. Right? That's raised to the 20th. Then we get the probability. Right? 0.5 raised to the 20th. That is 0.000000095. All 20 are girls, which with that small probability, right? 6 zeros, that's 954. Almost about just a millionth case, right? Then, as we mentioned before, when the probability is smaller than 0.05, that is very unlikely to happen, unusually low. Right, then we have decimal probability, so it's very unusual to get 20 newborn babies, all of them are girls, or 20 girls in a sequence, or in a row. Well, when at least one boy is being asked, if we do straightforward, that will be very hard. And we don't have the way to do that yet, right? At least one means one boy, or two boy, or three boy, or four boy, or five boy, all the way to 20 boys. Well, that's very hard. Even though maybe later we have a way to do that, that's still very hard. And what we have here is, if we think in different way, oppositely, at least one boy, the opposite of it will be no boys. Right, the opposite of at least one boy will be no boy at all from the 20, which means all of them are girls. That is the word called complement. So the probability of at least one boy is the complement of all of the 20 girls are up here. It's the complement of all of the 20 girls. That complement, how we find it, is 1 minus the probability of all 20 are girls, which is what we found in the first part. So we can just use the result. 0.954. That is 0.999990466, which is pretty much certain. Pretty much very close to 1. I don't want to say our probability is actually 1. Well, that is a certain event, but here it's very, very close to 1. How close it is? We have 6, 9. So in the figure. Okay. Right. So that is the 20 girls in row. Well, what happens if that is 2 boys and 18 girls? Well, that will be a little harder, because we don't know which 2 are boys out of the 20 births, right? It affects, of course, differently for the couples. Therefore, whichever the 2 boys coming out is actually making difference. We'll see that in our later chapter. It's actually called binomial distribution, right? But we'll see that later. For now, 20, same thing in a row, we just multiply them together, right? That's the only case that we can have 20 baby girls, and at least one boy will be its complement. Well, now rolling 2 fair dice. What is the probability, asking for what? That the sum is 7. Well, it's the probability that the first die, that the sum of the dice is 7, given the first die lands on 6. Right, that given part means, well, instead of, like we have seen before, right, instead of focusing on the whole 36 outcomes of rolling 6 dice, we only need, well, what we already know is that, well, the first die is landing on 6. So instead of focusing on the 36 whole outcomes, we're just focusing on the new sample, some sort of the new sample space that the first die is land on 6. So to see the new sample space, first on 6, we have the new sample space of 6, 1, 6, 2, 6, 3, 6, 6. So we have 6 outcomes for the first die is landing on 6. Right, so the thing after the given part is called condition, what we can see the material called conditional probability, which also we had seen before, the drug testing that only focusing on the 50 uses drug, and then we're focusing on that. Here is we know that while the first die lands on the 6, then we're focusing on this first die is 6 landing, first landing on 6 and the new sample space. Now what we have is only 6, 1 is the landing on 6. I mean the 6, 1 has the sum of 7. So the probability will be focusing on the new sample space, that's 6 items or 6 outcomes here, and inside that's only one can make it sum to be 7. So we get the probability of 1 out of, instead of 36, we have the given part of stronger condition or smaller condition, make the sample space smaller, which is 1 over 6. And that is given part is what we're focusing on now, and the new probability will have a different denominator instead of that. Right. So that is conditional probability, so called, and let's see definition. Right, the notation here is called probability of B given A. Alright, we have a short vertical line to separate them, and B given A is the probability of B given A is how we read it. That represents the probability of event first, given that well, the A is the condition here, so the probability of event B occurs given that the event A has already occurred. Right, so go back to the Venn diagram. The sample space was S, and we have two events, A and the B. Now saying is, well, the condition. Left. Right, the sample space, the event A, event B. Well, what we have is, well, we know that the event A will happen for sure, because that's the condition. And the shaded part is the event A, right? So the A and the B are overlapping in general. Then how the B happen is the middle part only, right? The middle part happen, then the event B happen when A happens, which the middle part is called the intersection. Right, so the couple example before we had seen was the probability of the conditional probability of B given A, right, which it can happen only when the intersection happens. So the number of ways that the intersection can occur over the number of ways the condition can occur. Right? So still focusing on the condition first. How likely the condition being occurred and how likely when the condition and the other event occurred at the same time. Right. So for this formula, if we divide the denominator and numerator both by the sample space, which actually we get is the probability, right? Sometimes to find the number of ways of the numerator and denominator is easier. Sometimes finding the probability is a little easier. Right, so that is the probability of A and B over the probability of A. The intersection over the condition, right? So that is the formula for conditional probability. And that is how B occurs, right? How B given A occurs is B occurs when, if, and only if the intersection occurs. That we can see from the Venn diagram, and that is both of them we can use as the formulas. Or still the table of what we have used before. 166 or 50 and 950. Right, so a couple of things being asked. So we have seen that before actually, right? Now let's do something else. Find the probability, get a positive result. Given that the test is that the being selected individual uses drugs, right? That one is the one we have asked.